Ladderane. In chemistry, a ladderane is an organic molecule containing two or more fused cyclobutane rings. The name arises from the resemblance of a series of fused cyclobutane rings to a ladder. Numerous synthetic approaches have been developed for the synthesis of ladderane compounds of various lengths. The mechanisms often involve 2+2 photocycloadditions, a useful reaction for creating strained four-membered rings. Naturally occurring ladderanes have been identified as major components of the anammoxosome membrane of the Anammox bacteria Planctomycetes. Nomenclature: chain length, chain length, chain length, length, chain length. Synthetic approaches have yielded ladderanes of varying lengths. A classification system has been developed to describe ladderanes based on the number of consecutive rings. The length of the ladderane is described by the number in brackets that precedes the word ladderane. This is equal to the number of bonds shared by two cyclobutanes and plus 1. A ladderane of 3 or more units can connect in a circle, forming a band, which can also be considered to be two interconnected parallel cycloalkane rings. These are called prismanes. Stereochemistry. Ladderanes have two types of stereochemical relationships. One describes the relative arrangement of hydrogen atoms at the fusion between two cyclobutane rings. These hydrogen atoms can be in either the cis or trans configuration. Trans ladderanes have not been synthesized due to the ring strain in these compounds. The second stereochemical relationship describes the orientation of 3 consecutive cyclobutane rings and therefore is only relevant to ladderanes of n equals 2. The two outer rings can be on the same face syn or on the opposite face anti of the center ring. Synthesis. Various synthetic methods have been used for the laboratory synthesis of ladderane compounds. The 3 major approaches are 1. Dimerization of polyene precursors, 2. The stepwise addition, 1 or 2 rings at a time, 3. And oligomerization. Several examples of ladderane synthesis are outlined below. Dimerization of cyclobutadiene. The dimerization of 2 cyclobutadienes can generate both the syn and anti-ladderane products depending on the reaction conditions. The first step in forming the syn product involves the generation of 13-cyclobutadiene by treatment of cis-34-dichlorocyclobutene with sodium amalgam. The reactant passes through a methylated intermediate before forming 13-cyclobutadiene, which can then dimerized to form the syn-diene. Hydrogenation of the double bonds will form the saturated syn-3 ladderane. To generate the anti-product, cis-34-dichlorocyclobutene is treated with lithium amalgam. The lithium derivative undergoes a C-C coupling reaction to produce the open dimeric structure. This intermediate reacts to form the anti-diene, which can be hydrogenated to form the final anti-3 ladderane product. Synthesis of a 4-ladderdiene. A different synthetic approach developed by Martin and co-workers has allowed for the synthesis of 4 ladderanes. The initial step involves the formation of a 2-ladderane from the addition of 2 equivalents of maleic anhydride with acetylene. The remaining 2 rings are formed from the Ramberg-Backlund ring contraction. Synthesis of long-chain ladderanes. Ladderanes with lengths up to 13 cyclobutane rings have been synthesized by Mehta and co-workers. This process involves the in situ generation of decarbonhexacyclobutadiene from its FeCl3 complex at low temperatures with the addition of steric Roman 4 ammonium nitrate can. Generation of the butadiene rapidly forms a mixture of n-ladderanes of lengths up to n equals 13 with an overall yield of 55%. All of the ladderanes synthesized through this method have one cis-syn-cis structure. This may be a result of the initial dimerization of 2 cyclobutadienes, which preferably forms the syn product, shown below. The further dimerization only produces the anti-product due to steric factors. Dimerization of polyene precursors. In these reactions, ladderanes are formed from multiple 2+2 photocycloadditions between the double bonds of 2 polyenes. A complication that arises from this approach is the reaction of the precursors through alternative more favorable photoexcitation routes. These side reactions are prevented by the addition of a chemical spacer unit that holds the two polyenes parallel to each other, only allowing 2+2 cyclobutane to occur. A common spacer used in these reactions is the 2.2 paracyclophane system. This is sufficiently rigid and can hold the polyene tails in close enough proximity for the cyclobutane to occur. Ladderane and colleagues have demonstrated that a supramolecular approach to covalent synthesis in the organized, solvent-free environment of the solid state can provide a solution to the problem of organizing two polyenes for an intramolecular reaction to give a ladderane. Specifically, by taking an approach to control reactivity in solids by using molecules that serve as linear templates, they have demonstrated the utility of co-crystallization of resorcinol 13-benzenediol, or a derivative, with an all-trans bisphorpyridyl poly, amine 4-popoly. Amine produces a four-component molecular assembly. The two polyenes are positioned by the templates such that the C bonds of the olefins lie parallel and separated by 4.2 a position suitable for the photoreaction. UV irradiation of the solid produces the targeted ladderane, with the C bonds reacting to form the fused cyclobutane framework. Broadband UV irradiation of two such hydrogen-bonded, four-component supramolecular assemblies furnishes the corresponding ladderanes stereospecifically and in quantitative yield in gram quantities. Biological background: ladderanes were first identified in a rare group of anaerobic ammonium-oxidizing Anammox bacteria belonging to the phylum Planctomycetes. These bacteria sequester the catabolic Anammox reactions to intracellular compartments called anammoxosomes. The Anammox process involves the oxidation of ammonium to nitrogen gas with nitrite as the final electron acceptor. Intermediates in this process are two highly toxic compounds, hydrazine in 2H4 and hydroxylamine in H2OH. The oxidation process involves the generation of a proton gradient on the intracytoplasmic face of the anammoxosome. Dissipation of the proton gradient is coupled to the phosphorylation of ADP through membrane-bound ATPases. Anammoxosomes are enriched in the ladderane lipids shown at right. Analysis of the anammoxosome membranes from the bacterial species Brocadia anammoxidans and Kuehneania stuttgartensis has revealed that ladderanes constitute greater than 50% of membrane lipids. The high abundance of ladderane lipids in the anammoxosome results in an exceptionally dense membrane with reduced permeability. The reduced permeability may decrease the passive diffusion of protons across the membrane that would dissipate the electrochemical gradient. This would be especially detrimental to Anammox bacteria due to the relatively slow Anammox metabolism. The decreased permeability has also been hypothesized to sequester the highly toxic and mutagenic intermediates hydrazine and hydroxylamine, which can readily diffuse through biomembranes. The loss of these key intermediates would damage key cellular components such as DNA, as well as reduce the catabolic efficiency of the cell. Synthesis of ladderane lipids. A naturally occurring 5-ladderane lipid, named pentacycloanomoxic acid, has been synthesized by Corey and coworkers. The first step in this reaction involves bromination followed by cyclization of cyclocatatrine to form a cyclohexadiene. This cyclohexadiene is trapped by dioxyl azidocarboxylate. Functional group modifications are made to produce a cyclobutane, which is elaborated through a 2+2 photocycloaddition with a cyclopentanone to produce a second cyclobutane ring. Protection of the carbonyl group, followed by an 2-extrusion reaction, yields two more fused cyclobutane rings. The final cyclobutane is formed by a Wolff rearrangement, and the alkyl chain is installed by a Wittig olfination. In 2016, Burns and co-workers at Stanford University reported an enantioselective synthesis of both the 3 and 5-ladderane lipid tails and their incorporation into a full phosphatidylcholine lipid. Both routes leverage a small 2-ladderene building block bicyclotwo 0.2 hexene prepared by a Ramberg-Backlund reaction. The route to a 5-ladderane containing fatty acid involves dimerization of this intermediate form and all anti-5-ladderane hydrocarbon. CH chlorination by a manganese porphyrin catalyst and subsequent elimination introduces unsaturation to produce a 5-ladderene. Hydroboration and a Zweifel reaction install the linear alkyl group. The route to a 3-ladderane fatty alcohol begins with a 2+2 photocycloaddition between a brominated benzoquinone and bicyclotwo.2,0-hexene. Elimination of HBr and addition of an organozinc compound installs the alkyl alcohol. A hydrazine-mediated deoxygenation reaction followed by hydrogenation with Crabtree's catalyst effects reduction to the cyclohexane ring. References